going to be a good summary of what he is going to talk about. The title of his talk is The Replica-dynamic Correspondence in Finite Dimensions. And okay, looks like you're set. Please go ahead, Jorge.
Okay, so it's not about the meaning of time, so that it won't be that philosophical. Anyway, can you hear me? Yes.
Yes, perfect.
Okay. So very quickly, I suppose that you've got many talks on this. A quick reminder of the Parisi scheme. So we have the states of our systems, which are typically shown in this way. As you know, there's the replica trick, whereby you want to calculate a logarithm and you calculate instead the powers. Then there is the Parisi ansatz that tells you a specific way to implement this. And so the replica trick plus Parisi ansatz is, we know now, the good solution for example, mean field spin glasses. So as you probably all know, the point of the ansatz is that you are supposed to guess what is the form of a matrix, which is a matrix of order parameters. The only little problem is that the size of the matrix goes to 0 when you want to do the continuation. And it was the scheme that in the end was the good one, was devised by Giorgio, where he just broke it in blocks, as you can see here. A color means that the value of the matrix is the same within each color. And the sizes of the blocks stay fixed. As the matrix goes, the size of the parent matrix goes to 0. So as you maybe most of you recall, this is one of the strange moments of your life when you study this for the first time. This scheme, mad as it seems, is successful. And so the elements that have been taken into account, have to be taken into account, are the sizes of the blocks. There can be blocks and blocks within blocks and blocks within blocks, and the actual values that the correlations take in those blocks. At the end of the day, from these parameters, what you get, what the theory gives you, is the actual values the correlation can take. This is a probability distribution in equilibrium, and the x's, the sizes of the matrix, are interpreted as probabilities or related to probabilities. And what is an output that wasn't at all expected, and it was a big surprise, is that the ansatz carries with it the notion that all possible triangles you can make between states are isosceles. So if I consider 3 states and I look at the overlaps, what the ultrametricity property means, the ultrametricity is just a name, is that when I take the further apart, the ones that are further apart are at exactly the same distance. So that this distance and this distance are the same. And this is true for all triangles. So we get 2 things. We get the probabilities here, the actual values that can be taken, and the fact that all triangles are isosceles. Okay, so this is the Parisi ansatz in, say, 2 minutes. Of course, I didn't mention, but this curve, instead of a family of deltas, could be a continuous curve. And in fact, for Sherrington-Kirkpatrick, it is. Okay, so now the dynamical picture is the one, of course, that things do in nature. And I will present to you 3 versions of the dynamics because the 3 of them are nice to implement even numerically. One is the aging, another situation where you just quench a thing and the glass cannot equilibrate. So it evolves and evolves and evolves. It gets older and older and older, but it never reaches a state in which you can say, the thing is finished, I'm in equilibrium. The other possibility is to study your system subjected to weak shear. And you will, as I will mention, weak shear keeps the system at a constant age, let's say. It doesn't allow it to get older. or the same effect is obtained with slowly changing interactions. So aging. So you take a plastic ruler, you make it from polymer melt, you created it now, and then you do the following experiment. You pull at time t waiting, the waiting time, traditionally called this way by the experimentalists, you pull from the ruler, and what you see is first, there's going to be a stretching that is always the same, universal. It's the quick response of the system. This one doesn't change very much with the waiting time at which you did the experiment. But then the system will creep to a new length slowly, and this speed at this regime depends linearly, roughly, with the waiting time, meaning that if you do the experiment after a minute, the creep time, this intermediate time, will take around a minute. If you do it after a day, it will take around a day. If you do it after a year, it will take about a year. And this experiment has been repeated up to 3 years, showing that something is going on inside the ruler that you don't see, and you only see it in this creep experiment, but the ruler knows that what its age is. Although it doesn't seem to change a lot, and many properties seem to not change anymore, the ruler knows. And there is no chemical change at all. And in fact, spin glasses do exactly the same thing. So the big parameter here is the waiting time. If you want to make a theory that can be tractable, you want to do it for longish waiting times. But longish does not mean infinity, because the thing goes on, and aging goes on forever. So long waiting time, yes, but not infinite. Here you have the Strauch experiments, which I showed before, put in context. So this is the response, the integrated response of the system, so how much it creeps. And this is log of time. And the first part here is where the sound waves live, the ultraviolet, if you want. That one doesn't change a lot with age. But then you have this part, which is the creep regime, which changes dramatically with the waiting time at which you started your experiment, at which you decided to stretch your rule. There is another way to do the same experiment, also done by Strauch at his time, is to, instead of taking your ruler and repeating these experiments, to every week on Fridays, you take your ruler and you bend it back and forth 3 times, and then you put it back. And you do this all along. If you do this, then one thing that Strauch observed, and now we understand perfectly well, this has a rejuvenating effect. And so you get these experiments just as they are, but now the waiting time, the age, will be frozen at around a week. This is because every week you shear the system a little bit. So shearing, what it does is it doesn't allow you to equilibrate, but it does stationarize your situation. So your ruler is now a week old forever, but that doesn't mean that it's in equilibrium. If I stop doing on Fridays the bending back and forth, it will go back to aging. And another method, which for a ruler you cannot do, but for a spin glass is very convenient, is to simply change the disorder. So you know that interactions can be plus or minus, and if now every week you change a few of the interactions randomly in sign, you have the same effect as bending back and forth the ruler. The system will be old, out of equilibrium, but it will not age further. Why? Because you are changing it, the optimization it has to achieve by changing the couplings. So it's kind of surfing at a constant age. Okay, so these are the 3, or at least these are 3 ways of making slow dynamics. So to recap, the first one is aging, where the parameter is self-generated. It's the waiting time at which you're doing the experiment when you created your system. If you do the experiment a month later, its waiting time is a month. Or the shear rate, this was the weekly bending back and forth the ruler. The smaller and the weaker the shear rate, you will be stationarized in an older age. So you will look always old, or if the shear rate is even smaller, you will look always constant, with a constant age, but older. And the same exact thing you can achieve just by changing the parameters very slowly, changing the interactions very slowly. So the three parameters are the waiting time, or the shear rate, or the rate at which you change the interactions. We will be interested in this being big, and this being big. And one thing you discover, and it was quite an amazing thing, is that when you go from one of these situations to the other, in fact, what you're doing is you are showing the same film. What is going on inside of the ruler or the spin glass is statistically the same thing, but you are changing the speed at which you are passing this film. So the correlation, which was a function, for example, if the system were aging, of the times, now the times are sped up in some way, and what you are changing is the speed at which you're showing the film, which is to say you're changing you're affecting a time reparametrization. So so what you get is that your functions, which depend on times, you can solve them. You can get a result which is very stable with respect to whatever you do to the system, provided it's not enormous. But the slightest thing you do to the system will change the speed, and in a nonlinear manner, at which the situation is happening. So this is what is called reparametrization softness. It was, as far as I know, mentioned for the first time by Sompolinski and Zipeliu some 40 years ago. I think this is the first reference, at least the first I know. And they realized technically why this was happening. Maybe they didn't make all the connections because many of these things were not known in the physics, but it is a physical phenomenon of glasses. You can very easily change the global speed at which all variables move, but the relation between them, as I always say, the moment when Ingrid Bergman gets onto the plane and Humphrey Bogart is looking at her, the moment at which this happens, they change, but she is always concomitantly with him. At that moment when he is getting up the plane, she will be down. So when you compare facts to facts, you see the same thing, but the moment in time can be stretched by very small perturbations. This is, if you want, one of the most central facts of glasses. I will try to convince you that perhaps it is the central fact. Okay, let me add one little thing that I need technically. You can study the correlations of the system just by, for example, in the case of the ruler, looking at how the polymers moved, or you can study the response. The response is exactly what Straub did. You pull from the ruler and you see how it responds. And you can plot correlations versus responses, and you know that if you are in equilibrium, the integrated response versus the correlation gives you a straight line with gradient temperature, and this is the fluctuation dissipation. So these two are very closely related when you're in equilibrium. They are linearly related, but out of equilibrium, you don't know. So I am going to go back because we will need both sets of parameters, both correlations and responses to discuss our. Okay, so let me go back to reparametrization. So what do I mean by what is reparametrization invariant? What would be a quantity that doesn't change? Remember, you want to compare the moment where Ingrid Bergman is climbing the plane and when Humphrey Bogart is crying. So you have to relate facts with facts and factor the time away. So if the system has a correlation, could be something, and another correlation, if you express a correlation in terms of another correlation, that is a reparametrization-invariant fact. The times have gone, and you get simply a function that relates facts with facts. So this is a quantity that is robust with respect to reparametrizations because it simply does not contain the time. The same thing, this is when you plot the response versus the correlation. So it is a two-point function in terms of another two-point function. And you can plot them one against the other. This is another reparametrization-invariant fact. And it is very important because the curve that gives you integrated response versus correlations defines this X parameter, which will be very important for us. It is something that substitutes the fluctuation dissipation theorem, but we are out of equilibrium, so we don't. And the third one is, imagine that I have 3 times. Time 3 and time 1 are very far away. And I instead consider an intermediate time 2, and I see what triangle the thing makes. So I have time 1, time 3, which is the largest, and I have these 2 intermediate correlations. If I can express the big side of my triangle in terms of the 2 smaller sides, this creates a triangle, and you see that time has been factored away. It's a correlation in terms of another 2 correlations. So also this one is a reparametrization invariant thing. We will need these 2 because these 2 are the ones that make the bridge with Parisi's solution. So one possibility you can have, and this is what happens in the Sherrington-Kirkpatrick problem, is that when you draw a triangle this way with 3 sides, these are the 3 times at which you're looking at your system, and you consider the correlations with an intermediate time, the big side has as a length, or as a correlation, the smallest correlations of the 2. What this means is very simple, in fact. It means that if I have to make a big step and I decompose this into 2 smaller steps, the biggest of these 2 smaller steps costs almost all the cost in time. So this is part of the dynamical solution of the Sherrington-Kirkpatrick model. And as I will show you, it is a property that is extremely easy to verify. So we have this reparametrization invariant quantities, and we are saying that the system is soft with respect to reparametrizations. So it doesn't cost me a lot to change the speed at which the film will pass. So what happens in StatMech when I have an almost symmetry? So reparametrization of time is an almost symmetry. It costs very little, although not 0, to change the speed at which I'm passing the film, which is a bit like, this is a metaphor, this is not literally what our situation is. Imagine you had a system that almost has a symmetry. It's a Mexican hat, as you can see, but it is slightly tilted. And so I have modes that are almost for free, which are these ones. If it were a true symmetry, they would be completely for free. And you have modes which are more costly. So same picture here. So this is a metaphor of what we have. What we have in reality is quantities that are very robust with respect to reparametrizations. So these ones a reparametrization doesn't affect. They are quantities where time has been factored out. And then very easily you can change the reparametrization. Of course, the symmetry is not just a rotation. This is just a metaphor just to take into account this. So now in the language that is fashionable now to say these things, you would call these ultraviolet excitations, because they are hard, the system doesn't want to change in that direction. And these would be the infrared, which are, in our case, the reparametrization. Okay, another small subject. What do systems do when they're out of equilibrium? So what does a mean field system do? A system that has a Parisi solution for the statics, what does it do when I do its dynamics? So in equilibrium, as you know, I have the correlation, I have the response, and when I plot one against the other, eliminating time, I get the fluctuation dissipation here. Now, if I do the same out of equilibrium, something very, very strange and unexpected happens. You get an aging situation. This is precisely the aging situation I was describing before for the correlation and for the response. This is the waiting time, 1 hour, 10 hours. But then when I plot correlations versus response, what I see is that this part, the fast part, happens indeed as if I were in equilibrium, but the slow part happen, and this is the amazing part, as if they were in equilibrium at a different temperature. This is very, very surprising. Where does this temperature come from? The usual temperature, this one, is the bath temperature. But this effective temperature is chosen by the system itself. So the system has developed an extra temperature. Why did it do that? Because it's out of equilibrium. If it were in equilibrium, it wouldn't be able to do that. If you are in equilibrium, you only have the bath temperature. So this is one of the things we have learned over the years. And we have also learned that you could have 3 temperatures, the bath temperature for the fast part, then another temperature for very long times, and then another temperature for very, very long times. And when you do the plot, you find indeed 3 lines corresponding to 3 different effective temperatures. But you can, and this is part of the whole scenario and the part of the solution, these temperatures, if they want to be different, then they need to happen at extremely far away timescales. So the morals of this is the system develops temperatures, it develops timescales. All observables in a timescale have the same temperature defined by fluctuation dissipation. But a thing that is very important is that if you want 2 different effective temperatures, then they can only be happening at very, very wide apart timescales. So this is what I will call multithermalization. The point is that there are 2 surprises. Well, the first surprise is that effective temperatures appear. The second surprise is that they coincide for all observables at a given timescale. And the third surprise is that you can have many, but then they have to be in very different timescales. So just a quick flash. This is ultrametricity for Sherrington-Kirkpatrick. One way of being ultrametric is this scaling. You can convince yourself that it has the properties of the triangles I mentioned. And when you try to plot this with a naive scaling, you get something that clearly doesn't work. Longer parameters, the curves are not converging to anything. And when you scale them correctly with the ultrametric scaling, you see that the curves very quickly reach a limit form. So morals of this is it's very easy to check the dynamic ultrametricity in a simulation. Okay, and now come a couple of surprises. So I have described to you the static scenario of Parisi, which concerns states, which are equilibrium states, and I have mentioned that dynamics never reaches those states. And then I discussed dynamics, which is off equilibrium. The system is flying near, but distinctly away from the equilibrium states. It has not been able to reach equilibrium. It is violating the equilibrium theorems in a very interesting and strange way, surprising way. Why should these two things be related? And in principle, one would say they shouldn't. Now, there are a couple of surprises. The first one is that, as many of you know, the Parisi function gives you the probability that I was mentioning at the beginning, is the derivative of the parameter x. Remember the size of the blocks with respect to q, the actual value you have in those blocks, and is usually introduced as a probability of having states at a certain distance q. But you can also introduce it as a set of susceptibilities. You add these are fields, nonlinear fields, and then it turns out that the Parisi function is a generator of these susceptibilities. It's another way to introduce it, and in many senses, it's a more controllable. You can do the same thing dynamically. This we did with Letizia Cugliandolo many years ago, and you get similar quantities, with the x being the effective temperatures that I mentioned a second ago. So formally, these two things resemble a lot, formally, but they concern, as I was mentioning, very different situations. In one case, you're looking at the few states that dominate equilibrium. In the other one, you're looking at what's going on when you're very far from equilibrium, albeit at long times. But formally, these two things resemble. And here comes a surprise. In a paper some, I don't know, 15 years ago, maybe, of these gentlemen, Silvio, Mark, Giorgio, and Luca, they showed not only that these two things played the same role, but in finite dimensions, remember it's very important in finite dimensions, then the dynamics and the Parisi x have actually the same values. So this is an incredibly surprising thing. How could this be so? So the argument, I'm not going to repeat it, but the main point is a nucleation argument. A nucleation argument is an argument that tells you that at long times, if you are in finite dimensions, locally, you cannot be very different from equilibrium. You are out of equilibrium, but still, you cannot have things that are very high metastable states, because there is always a nucleation that would kill those. So with this basic idea and a series of arguments where a series of tricks to adjust things, they showed that these two things, dynamics and Parisi, so this on this side contains the effective temperature, this one contains the probability distribution of Parisi. These two things are in a one-to-one correspondence in finite dimensions. So they did a couple of papers, as I said, some 15 years ago, and this is where it remains. I have very recently completed this argument because the question remained open: is it true for ultrametricity? Is it true for triangles? Remember, there are two elements, the axis and the fact that you have ultrametricity in Parisi situation, and you have a similar situation in dynamics where you have effective temperatures and you have the question of separation of timescales. Is this second aspect of separation of timescales remained open, although they did suggest that very likely it was also true, but they left it open at that time. So just following their steps and just changing a little bit the generating functions, and with the same hypothesis and the same strategy and the same ideas, I have shown very recently that also ultrametricity is in direct relation with Parisi ultrametricity. Dynamic ultrametricity and Parisi ultrametricity are one-to-one also. So the fact that you can have temperatures that are different only at very widely separate timescale is in a one-to-one correspondence with the fact that there is ultrametricity between two blocks of the Parisi vector. So this completes the correspondence. Okay, so bear this in mind. There is a one-to-one correspondence now that is complete between the Parisi solution in finite dimensions and the dynamic scenario I described in finite dimensions. Okay, so let me go back to the reparametrization softness. This is a property of dynamics, not so much of statics. But let me go back to it and try to convince you that it is a very important thing. It's not just an accident. So, as I mentioned already many times, there are two or more timescales in dynamics. There is a temperature for each timescale, but these have to live in very widely separated timescales. It is not allowed to have two observables that have different effective temperatures in the same timescales. If you have that, then the whole system collapses. The dynamical scenario collapses, but as it is in a one-to-one correspondence with a static scenario, it brings with it the collapse also of the Parisi scenario. So it is doubly important, and this is why I insisted on the dictionary. So, okay, so now I take two systems. These are two glasses that I connect to a thermal bath with a temperature T. They will have a fast temperature that will be the one of the bath, but they are constructed separately such that one has an effective temperature and the other one has another one. It's not hard to do. And now I connect these systems. I make a linear coupling between the two. So now I have a problem. If these two things happened in the same time scale, which I could have constructed two systems such that their slow time scale is equally slow, now I connect them, but now I have only one system. It is connected, weakly connected, but it's a big system, a bigger system. But now this system has a conflict because it violates the property I was mentioning before. The system will have things that have a given temperature, other aspects that have another temperature at the same time scale. So something is very wrong here because I also mentioned that this infinite dimension is in a one-to-one correspondence with the Parisi ansatz. So if this one fails, the Parisi ansatz fails too. So we have a real problem. A weak coupling of two systems satisfying the Parisi ansatz do not satisfy the Parisi ansatz. This sounds very worrying. And in fact, what happens is no, there is something that saves us in this, like in the last second, which is that the system, it seems almost like magic, the system will arrange itself so that the hottest temperature becomes even slower than the intermediate temperature. And now the scenario is recovered because the system has rearranged its time scales so that they don't overlap anymore different temperatures. This has saved the dynamical scenario, but by inference, it has also saved the Parisi scenario. But how could this work? How is it possible that just by using a very small coupling, my timescales have completely rearranged? Well, the answer, you will guess it now, is that precisely because of reparametrization-invariant, it costs very little for this system to pass this part of the film much slower, and for this one to make it a little bit faster. And because this is an almost zero mode, this is done with even infinitesimal coupling. So the ease of the system to make parts of its film go faster and slower is essential for the consistency of the dynamical scenario with multithermalization. And because of the Franz, Mezard, Parisi, Peliti argument as I completed it, it is also fundamental to make the Parisi scenario itself consistent in finite dimensions. Because the inconsistency of one of the two would bring the downfall of the other because of their one-to-one correspondence. So once again, this is arguments for the reparametrization invariance to be so important. So if this softness is so important, we should think a little more about it. And there's now another reason why we should, which I will tell you in a second. So what do you do when you have a system that is almost free in a soft direction, but it's very hard in another one? Well, as a physicist, you know very well, you write a sigma model where you keep these ones fixed, and the only dynamical variable in your system is h, is the soft thing. So you would write an action, which is an exclusive function of the functional of the functions h. This is the sensible thing to do when you are under such situations. And given that what we already said, and given that we believe that this is central, the reparametrizations are very important, this is the natural thing to do. So let me tell you a bit the story of this. The first to try to do this is these people here, Castillo, Chamon, Culiandolo, Kenneth, in a series of papers. I recommend them highly. They try to write an effective dynamical theory where everything, let's say the free energy, or call it, or the action, is exclusively an action that is a functional of the reparametrizations. And such theory, I believe that there are reasons to think that what they did is not complete, but they studied it in great detail and even numerically discussed it. This would give you an effective theory that will be a theory of shear response, aging, and fluctuations. So this is, there's plenty in those papers, but it's still missing some elements. In statics, one could ask the same thing. So reparametrizations are a bit more abstract in statics because they concern the replica space. They do not concern time. And it's a bit abstract to see what you mean by that. But in any case, something of the sort was attempted by Edouard Brezin and Cyrano de Dominicis in a couple of papers in those years. They attempted a first step. They found some problems. I would like to say that a word or two about that in a while. It's incomplete too. So these two things are have to be read, but they are in a way still incomplete. On the other hand, there is an extremely successful application of these ideas, although presumably not, these people were not aware of the precedents. If you do this in imaginary time quantum dynamics, so you have a spin glass, really a spin glass, the one that is used is called SYK, so it's Sashdev-Ye-Kitaev. And you do the same, exactly the same I was mentioning, only that in Euclidean time, you write a theory for the reparametrization. It turns out that this has been done to the bitter end, and the complete theory is your theory of fermions, which is what you started with, a fermionic spin glass. And the theory that only contains the action of reparametrizations is playing for them the role of the gravity dual of the theory. Now, don't ask me why I call it gravity dual. I call it gravity dual because they call it gravity dual. It's obviously the low energy, almost free excitations. And it turns out that the same, but exactly the same idea that these guys had and that these guys had has been picked up in this case, and to an enormous success, because they constructed this way a toy model of duality between quantum field theory and gravity. In this case, this was a brilliant intuition of Kitaev. This was successful till the end. So this is why, in part, I think that this deserves to be revisited. Also because in the light of the success that has happened here, one should feel more encouraged. So all in all, just I wanted to mention is that, okay, so what we have learned is reparametrizations, two things. First of all, the connection between statics, equilibrium, and dynamics that was started and mostly done by Franz et al., Franz, Mezard, Parisi, and Pellitti some 15 years ago is now complete. So there is, in finite dimensions, to the extent that the hypotheses are good, there is a one-to-one relationship with both. Mainly in dynamics, but also to a certain extent in statics, you discover that reparametrization softness is central to everything you're doing. So central that without it, the consistency of the whole scenario would collapse. And there is the idea that then what you should do is write a theory for the lowest excitations that is a theory where everything you have is the reparametrization, all the rest you have thrown away. So such a thing was attempted in dynamics, and I recommend highly those papers. And in replicas, I also recommend the other two papers. Of course, this one is very, very clear intuitively. This is a bit more obscure, but still I recommend them highly. And now it has very recently received all glory in the context of string theory, where the same, really the same idea has been extremely successful and carried to the very end, and with a lot of things that have been learned. So I think that this is just to advertise. It's definitely not low-lying fruit, and it's probably not a juicy fruit from the point of view of citations, but I still believe that this is a very interesting intellectual pursuit to follow. So thank you very much.
All right. Thank you, Jorge. Right on time. We have enough time to have a discussion. Are there any questions? I don't see any raised hands right off. But maybe I can start off. So in the Franz et al. Work, I hadn't sort of registered the role that you mentioned for being, or having to be in finite dimensions.
Yes.
And now, so the question I have is, I mean, all the experimental work you mentioned also, of course, happens in a regime where you have activated dynamics and, you know, not.
Yes, it has nothing. Yeah.
So can you elaborate on that? Maybe I'll just leave it to you to take that question.
Yes, I don't think activated, not activated has anything to do. It will still be, unless you tell me that activated dynamics completely destroys the structure of the solution and converts it into something else. In that case, of course, the whole thing I'm mentioning may fail. But if the dynamic / Parisi ansatz solutions survive activation, then that's the only thing I'm asking.
Right. No, so the question I wanted to ask is the fact that these results apply in finite dimensions, does it make a stronger case that they would also apply in the presence of activation? That was my question.
No, the point, yes, and they need activation to be true, but you are making the assumption that, I didn't mention this, but one has to assume that there is one system of which we know that the Parisi answer in finite dimensions holds, and of that same system, then we will know that the dynamical answers with separated timescale also will hold. And then we would be able to say that they are the same and they have a one-to-one correspondence, these two scenarios. Unfortunately, we don't have any evidence that is for sure that there is a system. It seems to be the case that spin glasses in 4 dimensions may well have a Parisi answer and a Parisi situation. So that's the place to start. They also seem to have separated timescales, but those are very primitive simulations of 20 years ago. But we don't know. It could be, we don't have any rigorous or certain results. We only have numerical indications. More than that, we do not have at the time.
Okay. Other questions?
Shrikant, there are questions in the chat box, I think from Vincent and Silvio.
Okay. Actually, we'll just take it in the reverse order. I'm sorry, I wasn't paying attention. So maybe, Silvio, you can go ahead and comment, and then we'll take the question of Vincent.
Well, thank you very much, Shri. Hi, Jorge. Very nice review. Actually, I have two comments. One on on the correspondence between statics and dynamics and finite dimension. At that time, actually, we were very much concerned about the problem of what we call stochastic stability, more than attempting to, push the correspondence till ultrametricity, which seemed, by the way, to us very, very natural, which is the problem whether, which is crucial in the argument, which is a problem about exchanging of limits. Actually, in the proof, you use linear response, and in linear response, you always need to be able to exchange limits. I mean, for example, notably in statics, you want to exchange the limit of perturbation that goes to 0 with thermodynamic limits, and in dynamics, you want to exchange limit of perturbation that goes to 0 and the infinite time limit. So the essential point is that those limits should commute in order to be able to push the argument to the end. So the other thing that I wanted to mention is that okay, you want to do a sigma model for zero modes of spin glasses. Now, okay, in dynamics, okay, you have reparametrization invariance, which is very clear. In replicas, you have the reparametrization invariance of replicas up to now has not have received a clear physical interpretation. On the other hand, you know that there are zero modes which are physical, which are, for example, the ones that you can get considering a finite number of true replicas and fixing the overlap between them, and then moving those overlaps. And those are zero modes of the free energy. And indeed, attempts to do sigma models of those zero modes, and notably the simplest one, which concerns just two replicas, have been performed, and actually do give. I mean, if you think about that, I mean, a paper that I wrote many years ago together with Parisi and Virasoro can be interpreted in that way, and it gives rise, if you interpret in the sigma model language, to a field theory which is not analytical in the basic field. In particular, it gives an exponent for the critical dimension, which is not integer. But okay, so it is not a complete sigma model for all the zero modes, but at least there are results for one particular zero mode that you encounter in spin glass physics.
Jorge.
Yes, no, okay, I agree with everything you said. I think that there are two possibilities. One is one could go back to try to go deeper and see what if if within the replica world one can write a theory reparametrizations. And if not, one can give up and do it in dynamics, and that's that. There's no problem with that. In dynamics, we know what it means. And in dynamics, we know also that people with SYK have been successful. So we have this precedent, which is more than interesting. So I would say that that's one thing that could be done. But yes, I agree with you. There are a couple of things we have discussed for very long. This with Silvio, I have to say. One of the things that I didn't mention is that one thing that you realize, this is for experts, is that a one-step solution in finite dimensions is very unlikely. It has to be very, very special. So much for the random first order model. It's very unlikely that you can have a one-step solution, because then it has to have marginality properties that are very, very unlikely in a one-step solution. And this with exactly the same arguments. So we do learn some things that are interesting, even for the practical applications.
So Jorge, can you just say a little bit more on that? Because I think in terms of mean field, the continuous RSB is the odd man out, right? By and large. So is that correct?
So the situation for me in real life, as far as I can say, is the following. In 4 dimensions, both dynamically and statically, for spin glasses, it can well be the case that a scenario a la dynamic / Parisi with full is valid. In 3 dimensions, I would say it's quite clear that no, and the scenario must be something else for a spin glass. And instead, in systems of particles that are supposed to be one step, a one-step solution, literally a transition to a one-step situation, if such a thing exists, it is very different from anything we know in mean field. One of the things, and here I'm going to be very technical, is that the one-step solutions normally are not marginal. The vibrations in a state have nothing special, they are gapped. And instead here, you need, for the theory to be consistent, that it is gapless. And this is completely unexpected of a one-step solution. So maybe there is a case where many steps is the thing that works. But in order to check such things, you should go very, very close to the transition in equilibrium. So this is going to be very tough. Maybe with the swap algorithm, one can do something. But probably with the swap algorithm, one can do something.
All right, so there are 2 more questions. Vincent Saxton, and then Sumilan Banerjee. Okay, I guess I have to unmute. Just give me a second.
Hello.
Yeah, please go ahead.
Yeah, it was just the last slide where you discussed very briefly a particular research direction. Could you just expand on that a little bit, and what technically it would amount to, and what the scope and goal would be? Because I didn't, it was just very, very fast, and I didn't quite get the idea.
Yes.
Yeah.
So sorry.
Thanks.
Which you mean just.
Yeah, briefly.
You mean when I did this one?
Yeah.
Oh, okay.
Yeah.
So,
and you know, overall, there's a question. SYK has worked out very well.
Yes.
And then what would it involve to do similar things for 3D or 4D? Yeah.
So okay, 3D and 4D is already a harder ball game, because not even these people have done it really in 3D and 4D. Their system is mean field, but one can imagine more or less how it goes. But even keeping at the level of mean field, theirs is completely mean field, fully connected. There's only time. they did it, and already to do what they did for mean field spin glasses, so really treat reparametrizations with an effective theory. This hasn't been done, and this is within reach. So it would be taking very much like taking the Maldacena Schenker Stanford paper, where they do this for SYK, and attempting to do a similar thing for example, the dynamics of spin glasses. There is a paper by Facchetti, Biroli, and myself, and Reichmann, where we explain the analogy, so you can see the bridge more concretely. But that would basically have to do with doing a lot of things that have already been done and successfully by these people. So that part is I think within reach. To do it still at the level of mean field in replicas, I think it should be possible. Silvia already hinted at something. But there's a lot of things to be understood, because time reparametrizations have a clear meaning in time. But we all suspect that something like that exists in replicas, but only that in replicas there is no time. It's some strange property of replica space. So that has to be, I think, clarified. But already in these two people, there is the suspicion that something like that is there. You can check their papers, and they already discuss a bit. But one could revisit all these things with things we know now that they didn't know then, and we could also revisit theirs, knowing what is missing. There's a term in their equations, although they did a beautiful study, there's a term that is missing for sure. So then one could go. This is at the level of mean field. At the level of finite dimensions, then, well, that's the next step once one knows how to walk, to try to run, and then write an effective theory, and then eventually see how one goes about renormalizing it. That's really dreams.
All right. Last question by Sumilan, and yeah, maybe a quick answer, Jorge.
Okay, so thanks.
Yeah.
Can you hear me?
Yes.
Yeah, so what I wanted to ask in this SYK business, of course, in the fermionic model, you don't break replica symmetry, right? And you derive reparametrization, Schwarzian action. Now, so is that like a problem in the case of spin glasses? I mean, you have to do it with the replica symmetry breaking somehow?
Not really. What you need is that you are approaching a parameter region where the dynamics becomes very slow. So in the case of SYK, as you know, the correlation goes like 1/t to the 1/2, and then then it cuts off with the temperature. So if you are at long times, then reparametrization kicks in. No? And in these problems, the same is true. So in fact, the only real thing you need is that the system is such that it chooses to have, in some limit, slow dynamics, and then the whole thing follows. You don't need more than that.
Okay.
All right. Well, thank you, Jorge. So I have one very quick clarification before we end. About Ingrid Bergman and Humphrey Bogart, I assume the relevant reference is Casablanca.
Yes. I assume a minimal culture from the public. Yes.
Just for those who.
Okay.
All right. Thanks very much, Jorge. So